let's go to the application of radioactivity, radiometric dating or radioisotope dating. I mean, we have to find a technique to determine the age of rocks and organic matter. In general, we have to use the natural radioactivity process, natural radioactivity decay of the unstable element. This technique is used to determine the date of materials such as rocks and organic matter. Let me explain. You know, in general, this method is called radioisotope dating. Why? Because we have to choose one parent element and one daughter element. You know, the parent is unstable, will decay to daughter stable element. At a time t, as we have a decay, we can apply the principle of Decay's law. P at a time t equals to P0 times exponential minus lambda t. You know, Pt is the number of parent radioactive element at a time t, and P0, P, we can say P0 is the initial number of parent element at a time t0. And T half is the half time decay equals to ln 2 divided by lambda. You know, lambda is the decay rate. So if you know the value of t half of lambda, and you know the value of p at a time t and p0, you can apply this equation to find t. It's the age of the matter. But in general, it's impossible. Only in the case of organic matter, you can apply this formula directly. We have to know only in the case of organic matter. We can, because, why? Because in the case of organic matter, we have to use the carbon as an unstable element. And we know exactly the density and the number of carbon in the atmosphere and in the human body and the organic matter. So only in the case of carbon, and which can be used to calculate the age of the organic matter, we can use directly this formula to calculate the age. But in the case of fossils and rocks, we cannot use this method. We have to apply another method. We talk about them in the next slides. Okay, till now, let me explain in general. In general, by this method of using the radioactive process, we have to use a parent element and a daughter element. Okay, and as I said before, C14 is used only in the case of organic matter. But in the case of rocks and minerals and any geological matter, we have to use uranium, for example, uranium, potassium, rubidium, and so on. Why? Why I cannot use the carbon to determine the age of rocks? Because the lifetime of the carbon is about 50,000 years. And the lifetime of the age of any rock, it's about many billion years. We cannot use the carbon of many thousand years to determine the age of an object of many billion years. We have to use an atoms, a radioactive atoms, for example, like uranium, potassium, rubidium, strontium, or no, strontium is a stable element. We can use, for example, uranium, potassium, rubidium. These are an unstable element with a half-time of many billion years or many thousand years. and we can use them to calculate the age of rocks. Let me start with the organic matter. So here we use carbon-14 dating. It's a method. We can use the radioactive element carbon-14 to determine the age of organic matter. It's in general. This carbon-14 dating method, it's called also radiocarbon dating, or radioisotope carbon dating. In general, we can use by this method the Decay's law, P T, parent atoms at a time t, equals to P0 exponential minus lambda t. Why you can use it? Because the initial number of carbon at a time t0 is known, so we can use it directly. Okay, before, let me explain the creation of carbon in the atmosphere. Why we have a constant value of carbon in the atmosphere? We have to understand very well the creation of this quantity of carbon in the atmosphere. First of all, we have a cosmic radiation in the outer atmosphere. In the planets, we have a cosmic radiation. It's called primary cosmic radiation. In general, we have about 86% of this cosmic ray of protons, and we have 2% of helium, and we have many other heavy particles. Okay, these particles will collide with atmosphere's atom, okay, to create a neutron. So the neutron is created by the bombardment, by the collision of the cosmic ray, the primary cosmic ray, with the atmosphere's atom. Second point, this neutron will collide, these neutrons will collide with nitrogen 14 atoms to create one proton and one carbon 14. This is the next step. Okay, so in the atmosphere we have C14, and also we have another isotopes. For example, C12. We have C14 and C12, two isotopes with atomic number equals to 6. These two atoms, these atoms can form carbon dioxide, CO2. And the living organisms, like the plants, can consume this carbon dioxide. And all the living organisms will contain both isotopes C14 and C12 in the body, in the plants, in the wood. And all the living organisms, we have some quantity of carbons, C14 and C12. And we have to know these living organisms have a constant proportion of C14 divided by C12. The quantity of C14 divided by C12, it's a constant value, is constant. Okay, now we are talking during the living organisms, where the organisms are alive. Now we go to the next step. As soon as a living organism dies, the absorption of carbon dioxide stops. The source of carbon will be stopped inside for the living organisms. So the carbon in general, C14, decays. So the quantity of carbon start to decay, as you see here with the time. While the carbon 12 remains constant in the sample, in the object. During the time, we get the same value of carbon. So here we have to compare the quantity of C14 divided by C12 for the living organisms and the same quantity for after the death of the objects of the same matter. When we compare these two values, we can find the number of these atoms initially, and also we can find the same number for the same sample, for the same quantity at a time t. And you know, we have the value of half-life, half-time, the period. It's about 5,000 years for the carbon. We can calculate the time t or the age of this matter. So in general, in the case of organic matter, we have to use two isotopes, C14 and C12, to calculate the age of all organic matter. Okay? Be careful here. When I talk about age, it means it's a period of time from the moment of death to the moment we find it. Okay? During the living organisms, we have a constant quantity of carbon-14. At the time of death, at this point is the initial point. After the death of the living organisms, we start with the age. We calculate the age to the point, to the moment we find it. This age can be calculated by the isotopes C14 and C12. Okay? We can solve a simple problem to explain this point. Let me explain also, before going to the problems, I want to explain one point. In general, when I say the number of undecayed atoms at a time t equals to the number of undecayed atom at initial time exponential minus lambda t. In general, the number of atoms equals to the number of mole times Avogadro's number. We can say equals to n for this element times Na. Okay, n is the number of mole. You know, the total number of atoms equals to n times Avogadro's number. Okay, so Na equals to n. Before this one, let me explain another point. If you multiply by lambda here and lambda here, so we get a new formula. First of all, we have P at a time t equals to P0 exponential minus lambda t. Equation 1, you can calculate it to find the age, the time t. The second equation, if you multiply by lambda here and lambda here, you know lambda p or lambda times the number of atoms equals to the activity. Okay, lambda n, we talked about n before. Lambda p is the activity. So we can say the activity at a time t equals to the activity initial times exponential minus lambda t. So also we can use, if I give you the activity initial and the activity at a time t, you can use it to find the age. Also, as we said before, P, the number equals to the number of mole times Na, okay, equals to number of mole initial, okay, times Na exponential minus lambda t. So we can Na with Na eliminate them. We can find this relation, the number of mole at a time t, which is equal to number of mole initial exponential minus lambda t. Also, the number of mole equals to uh, the mass of this element at a time t divided by molar mass capital M, which is constant for the carbon element, equals to M initial divided by capital M exponential minus lambda t. We can eliminate M with M. Also, we can have the mass at a time t equals to the mass initial exponential minus lambda t. So if I give you any one of these values, we can calculate the age. Okay, let's go to the application. Before the application also, we have another point to add. After the death of the living organisms, okay, you know, here, when we have the bones or the organic matter, the burial organic matter in the sand, here you will get some kind of beta decay of this matter, of this died matter. Okay, where the carbon 14 will decay again to nitrogen 14 by beta decay. So again, we can have nitrogen 14. So the carbon 14 is created by the nitrogen 14, and again, the nitrogen 14 will be created from the carbon 14 down after the death of the living organisms. So it's a cycle. It's a cycle between the carbon 14 and the nitrogen 14. Okay, let's say we have a simple example here. I give you the activity of bone residue where the activity at a time t equals to 90 becquerel. Okay, assume it was initially it means A at a time t0 equals to 300 BQ. And I give you the half time equals to 5,730 years. I ask you to find the age of the bone at the moment we find it. So we can apply the activity at a time t equal to the activity at initial time exponential minus lambda t. We can calculate t, which is equal to 1 over lambda ln A initial at A final. We can calculate lambda equals to ln 2 divided by t half. We have these values. So we calculate t, which is equal to 9,970 years. Okay, so the age of this element, of this bone, the age is about 9,970. So we used the carbon 14 to calculate this age. As property, C14 is a radioactive element. Second, the half-life of C14 equals to 5,700 years. And you know, the total lifetime of C carbon, the total lifetime of C14 equals to 40,000 years. Why? Because in general, for example, if we have 100 initially, 100 atoms of C carbon, after T half, after half time, we get, for example, 50. After half time, we get 25. After half time, we get 12.5. After half time, we get, for example, 6.25. After half time, we get 3.12. Half time, about 1.5. And so on. In general, after 7 half time, we get 0 unstable element. So in general, the total age, the total time of the unstable element, in general, about 7 times the half time. So 1, 2, 3, 4, 5, 6, 7. Okay. If we have 1 half time equals to 5.7, 5,700 years, the total life of this element equal to 7 times t half equals to 40,000 years. So in general, we can use the carbon-14 to determine the age of any organic matter during a time of about 7,000 years. We can have some between 40,000 to 7,000, 40 to 7 to 70. Anyway, here we can talk about the mass spectrometry later. This mass spectrometry, it's a technique, it's a device, can be used to find the value of C14 divided by C12. As you know, we have the organic matter will emit some quantity of C14 and C12. For the living organism, we have some quantity, and for the died object, we have also the same. We can calculate the activity by mass spectrometry. Okay, let's go to the second topic.